Okay, let's do one last problem involving Jacobians here. Okay, here's what I'm going to do. Let's go ahead. I'm interested in finding the area, the region R, bounded by the following curves. Y equals 0, so that's the x-axis. Y equals 1/2 x, so you can think about that. That's the line through the origin with slope 1/2, okay? X squared minus y squared equals 1, that's going to be a hyperbola. X squared minus y squared equals 4, that's going to be another hyperbola. We're going to use this following hyperbolic transformation to do this, okay? X equals u cosh v, y equals u sinh v, and I'm going to have u and v greater than or equal to 0. So we're going to make those non-negative here, okay? I'm going to work first on finding r star, so that's going to be the pre-image under the transformation t. In the UV plane, that ends up giving us actually the region under discussion. By the way, if you want to graph this on Desmos, you can do so, but here is going to be the region of integration. Okay, so there's the x-axis, there's the y-axis, and the two hyperbolas, or hyperbole, I guess, whatever the plural is of hyperbola. Okay, all right. So let's go ahead and start working them then. Let's see. Let's go with x squared minus y squared equals 1 first. Okay. Okay. Now what is x? X is u cosh of v, so that's going to be squared minus u sinh v squared equals 1. Okay, like that. Now you see a common factor of u squared out there, and then we've got the cosh squared v minus the sinh squared of v is supposed to be identically 1 here. Now do you remember that the cosh squared v minus the sinh squared v is, there's an identity for that. This is identically 1. So we've actually got this multiplied by 1 is equal to 1. So u squared is equal to 1. That implies that u equals 1, since what? I have u and v being non-negative, so in the first quadrant of the UV plane. So u is equal to 1. Okay? So that would be what? Usually we have our system down with u horizontal and v vertical. So u equals 1, that's going to be what? A vertical line in the UV plane, isn't it? Okay? What about the second hyperbola? It's so similar to the first one, this shouldn't really take us much more work here. The x squared minus y squared equals 4. Well, remember the left-hand side reduced down to u squared, so that I'm really looking at u equal 2. So there's another, what? Another vertical line there in the UV plane, so that was pretty easy. Now let's go over to y equals 0. That's the x-axis, right? Now y is u sinh of v. Okay? And if that's always going to be 0, that means the sinh of v is always going to be 0. And that would imply that what? V is 0. Okay? V is going to be the constant 0. Okay, what would that be? This would be a horizontal line in our UV plane. Okay. Y equals x over 2. Maybe this is a little more interesting here. What was y again? Y was, let's maybe bullet these. Okay. Y is u sinh v. Okay, I'll put the half out front, and cosh, u cosh v, right, for x. Okay, now let's cancel the u's. Okay, assumably you're when u's not 0, we can do that anyway, so let's make that look more v-like there. There we go. Okay, and then we would have the sinh divided by the cosh v is equal to a half. This is actually what? Hyperbolic tangent of v is a half. Therefore v is hyperbolic tangent inverse of a half. Okay. All right. Now remember, the hyperbolic tangent inverse of a half is just a number. Okay. So this is constant. So v is a constant also. Okay. So this is what? This is another horizontal line. Okay, so r star is going to be looking like this then. In the UV plane here, we had what? U equals 1. Okay. U equals 2, so we've got these vertical lines. Whoops, smearing there a little bit. Okay. Then we had V equals 0. So that's just what the U axis here. So let's put it down though. V equals 0. And then we have V equals the hyperbolic tangent inverse of a half. That's going to be positive, so I'll make it above the U axis there. Okay, so you can see we're going to be integrating over this. So this constitutes that's our R star, which we're going to integrate over, okay, to get our original integral here. Okay, we're trying to find area. Okay. Now, what do we need next? Don't forget the Jacobian here, or Jacobian for those purists that don't like to anglicize thing. It comes from the German, so, okay. Well, let's remember what this is first. We're going to be doing this, right? Okay. All right, and you remember what it looks like here. Okay. Okay. And remember, x was u cosh v. All right. So whenever I differentiate that with respect to u, leaving acting like v is a constant, we would just get the cosh of v here, wouldn't we? Okay. And then when I differentiate it with respect to v, acting like u is constant, you remember the derivative of the cosh is the sinh, okay? Not minus, just plain old sinh. Now we have to do the same thing with y here. Differentiate that with respect to u, we get sinh of v. And then we want to differentiate that with respect to v, we get u cosh of v. Okay? Now, when I do this, take the determinant, it'd be u cosh squared, right, of v, taking the product of the main diagonal elements, minus the product of the off-diagonal elements. And then you've got u cosh squared v minus sinh squared v again. And you remember that that was identically 1, so we've got u for our Jacobian. In our theorem, we're supposed to take the absolute value of the Jacobian. So that would be the absolute value of u. But in our problem, notice that we're confined to the first quadrant of the UP plane, so that we'll just go ahead and put u there. There's not going to be any point in taking the absolute value of a number that's non-negative here. Okay? So let's go ahead and find the area. Okay? Now the area, you understand, would have been what? The double integral over r of essentially 1 dA, dx dy, or dy dx, right? Okay, you could even drop the 1 there. You see what it is. But that's going to be what? The double integral over r star of that same integrand in terms of u and v, which is still the constant 1. But don't forget that you need what in here? Don't forget that you need that guy, right? The Jacobian in there. So it's 1 times, okay? Du, dv, or dv, du, doesn't really matter here because we're doing it over a rectangle. There should be no advantage one way or the other here. Okay, let's go ahead and do it with respect to u first. Okay, so we've got u du and in dv. Where's u going from and to? U's always going from what? 1 to 2. And v is going from 0 to tangent inverse, hyperbolic tangent inverse, I should say, of a half, so that funny number. Okay? 0 to hyperbolic tangent inverse of a half. Let's see, that's going to be 1/2 u squared from 1 to 2, and then that'll be dv, what constant do we get there? We get the integral from 0 to tangent, hyperbolic tangent inverse of a half. Let's see, that's 1/2 of 2 squared minus 1 squared. So that's 3 halves, isn't it? Okay, I think that's 3 halves dv. Okay, so it's 3 halves. When we integrate dv, we just get v, and v is going from 0 to the tangent inverse, hyperbolic of a half. So I think we can do that in our heads. We get what? 3 halves hyperbolic tangent inverse of 1/2. And then you could compute the exact value of that in terms of logarithms if you wanted, but I think I'll just leave it that way. Okay, nice and compact. There you go.